In this video, I will explain how to extend a linear regression with two input variables TensorFlow code into regression using neural networks. So this will be regression, and we will still use the PyMet IBT's dataset, but then this time, instead of saying, can we predict age knowing blood pressure and BMI, we want to say, can we predict age knowing everything else, knowing all other variables. Now, in case of linear regression, we know that we load the dataset first and then open the dataset using pandas, check few rows, then load the data into a NumPy array, build a model with, if we have two variables, input dim equals 2, and then do the training using x equals our input x and y equals our output variable. And then we can make predictions using model.predict, and then plot true versus predictions by drawing a scatter plot. So now let's see how we can extend this. So we will once again start by downloading the data set, and then check the first few rows using pandas. And then we will also load the data using NumPy into a NumPy array, but then instead of selecting specific columns, we will instead load all the rows. But then after loading all the rows, what we will do is select all the columns except for the age column as our input, and then the age column as our output. So for this, I'm going to set x equals my data set, give me all rows, but then in columns, give me columns number 0, 1, 2, 3, 4, 5, 6, skip 7, and then 8. So this becomes my x, and then for my y, this is data set, and then give me all rows, and then my 7th column, which is actually the 8th column, but column number 7. So then let's verify that we have this proper, we have this data into x and y. So I'm going to print first few rows of x. And here we have our x. Let me print the first row of x. So this number clearly is 6148, and then it has everything but the a's. And let me also print y, the first row of y, and this has the first a's value, which is 50. So we have our input and output now. Now the next thing that we want to do is change this model parameters so that it works to accept all the input variables. Also, we want to grow this model into a larger neural network model. So my input dim actually should be the shape of x, which has 1, 2, 3, 4, 5, 6, 7, 8 columns. So either I could set it at 8, or I could even do len and then x, the number of columns in the first row. So this gives me my input dim. And now what I would like to do is add a few layers to this model. So I can simply copy this line and paste it 2 times, and also make the first layer have 8 neurons in it. The second layer have 4 neurons in it. This input dim equals the length of the input only stays in the first layer. This also goes away. Now it's also a good idea to actually make the non-last layer non-linear. So I can do ReLU here to make it non-linear. This also has to be ReLU. If I'm always predicting positive values as my output, I can also set the last layer as ReLU. So now our neural network model is ready with 8 neurons in the first layer, 4 neurons in the second layer, and 1 neuron in the last layer. Our loss can still stay as mean squared error. We have optimizer, RMS prop, everything stays the same. We have input x, output y, and verbose equals 1. So now we are actually ready to train the model. So let's do the training. So it looks like our loss has almost close to settled around 80, 81. So I'm going to label my true labels as true ages and obtain predictions by doing model.predict. Then as usual, we can do a scatter plot between true and predicted by drawing a scatter plot. So Here we can see that on x-axis we have true edges, and in y-axis with the predicted edges, and looks like they're quite okay correlated, quite better than how we did when we only had one or two variables as input. Now, so this is a visual way to compare true versus predicted. We can actually also come up with quantitative metrics to evaluate our models. And one really good way to evaluate regression predictions is to evaluate using mean absolute error, MAE. So I can do diff equals absolute of true edges minus predictions. Now it's, remember, we have to flatten the predictions because this is a 2D array. We have to flatten this into a list. So now we have diff as the list of the differences between true and predicted. So I can print the first few values of this diff array. And here's the difference between true and my predictions. Now to calculate mean absolute error, what I can do is simply calculate diff dot mean. This gives me the mean absolute error, so 6.5. In other words, overall, my model has an error. My model predicts edges by approximately 6.5 years off. So it could be wrong on average with 6.5. I can also calculate the standard deviation of my errors. So I can do diff.std, and then this gives me the standard deviation of the errors. Now, looking at these predictions, I can see that my model in a way correctly predicts smaller values more accurately than these larger edges. For example, these edges between almost 55 to 75 are always predicted to be between 20 and 50. So in other words, my model is biased towards correctly predicting smaller values of edges rather than larger values of edges. So these are things that you want to carefully look at when evaluating your model. I can also play around with my model.compile methods parameters by changing the loss. So I can change the loss from MSE to MAE and see if it improves my mean absolute error. So the current mean absolute error I have is 6.5. So let me see if by changing this loss to MAE, if I get anything further better. So I can also increase the number of epochs to 512. So let's run this. And now let's make the predictions and then again draw a scatter plot. So it looks like this time the model almost failed to learn anything. And then I can go back and look at the loss to see that actually the loss didn't improve at all from the beginning. So for some reason, MAE does not work well with the settings that we have. I can try changing my optimizer to something like SGD to see if it improves, if it does anything better. I'll roll back my epochs to 256, and I can see that already that the model is almost not learning anything. I can also try mean squared logarithmic error, MSLE. Now, adding log actually does a few things differently in this case. Now we can also make the predictions again and compare the plots. So this time the plot looks similar to how we had with mean squared error. Let's calculate the mean absolute error. So earlier we had 6.5 and this time it is 6.7. So this is how you can play around with the various parameters here. Now if I change the loss to MAE and try a different optimizer like NADM and see if this can improve the loss. Let's see what happens. So actually this time the loss seems to be going down. And with this setting, actually, I get a slightly better performance, at least better than what we had earlier. So let me calculate the mean absolute difference. So this is actually 6.1. So we actually have a slightly better mean absolute difference than what we had with the other settings. So this is how you can play with the various parameters in the model.compile. I can even change the number of layers in the neuron, increase the number of neurons, increase the number of layers, and play around with it until I get better values.